In this demonstration, we'll show how interactive physics can be used to create a model of a simple machine. The objectives for the demonstration are going to be to show how interactive physics can be used to easily create a model that can be used by students to investigate, explore, and understand concepts in physics. This will be an example that can be used to teach principles of levers. We'll also show how a player-only version can be saved and can be used by the teachers and students. It allows the students to interact with the model but stay on task. The steps involved in creating the model for our demonstration are going to be as follows. First, we'll create objects. We'll attach pictures to objects. We'll add constraints. We'll add interactive input slider controls. We'll add a measure, and finally we'll add animated force vectors. Before we get started, let's do a simple review of how to calculate the mechanical advantage of a lever. There are two approaches we can use. The first uses the resistance force and the effort force. The second approach uses the effort arm and the resistance arm. For our demonstration, we're going to use approach number 2. So let's go ahead and get started with our model. The first thing we'd like to do is set up the workspace. We'll click on View, Workspace, and we'll turn on rulers, grid lines, and XY axes. These allow us to see where objects are being placed, relatively how big they are, and where they are in relation to the origin. The next thing we'll do is establish the units that we'll use for our model. We can click on View, Numbers and Units, and we can specify a unit from the drop-down setting here, or we can also select more choices and customize units to our needs. For this example, we're going to use SI degrees. To begin drawing the objects, we'll come over to the Object toolbar here and select the Rectangle tool. As we move the mouse over the viewing area, we can notice that on the bottom there's a tracer that follows on the ruler, depending on where our mouse is positioned. What we'll do is we'll move the mouse to approximately y equals 0 and x equal -4, and we'll click the mouse button and release it. We can drag here and begin creating a rectangle, and we'll move to the other side to a +4, and it doesn't matter what the y thickness is here. It can be anything you'd like it to be. Click again, and we have a simple rectangle. For fun, if we hit the Run button, the object just simply falls with gravity. If we reset, we can come down here and we can grab the playback slider, click, hold, and we can drag our mouse and drag the slider back and forth and replay the animation. Let's go ahead and continue and draw the remaining 2 objects in here that'll represent the objects resting on the platform. For the object here, which will be our resistance, we'll use a square. We'll click on the Square tool, and then we'll use the grid spacing here as a guide to create our body. Notice that when we move over certain points here on the grid, we have the grid snap turned on, and so these points sort of wake up, if you will, and we have an X there. Click. You don't need to hold the mouse button. You can simply drag your cursor over to the next point, which will be right here, and we'll click again, and we have another object. Let's do the same thing on the other end, except this time we'll use a rectangle tool, and we'll come over here, and as a starting point I'll use this corner edge of the plank. Click, release the mouse, move the mouse roughly to this position here, and click again. Now, if we wanted to stop here and not draw the fulcrum and a ground part represented right here, we could simply add a pin joint to the center of this platform and be finished. To demonstrate that, I'll come over here on the Constraints toolbar, and I'll click on the pin joint, and I'll hover my mouse over the center of the bar. We also have Object Snap turned on, so it understands that the center point is right here. So we'll click on that, and then if we run our simulation, again we have gravity acting, and we have contact between bodies, so you can see those bodies remain on that platform. If I drag the slider toolbar back and forth, we can replay the animation. So let's go ahead and let's remove that pin joint. We're going to go ahead and we're going to add the fulcrum and the base plate just to make the model a little more visually appealing. And we'll come over here to the object toolbar and we'll draw a polygon representing our fulcrum. I'll move the mouse over the bottom of the plank here and notice that there's a snap point that wakes up. Click. Move my mouse to some arbitrary position. It really doesn't matter where you want to position it here. This is just for visual purposes. Click. Click again. And when we click back on our start point, it will close the polygon. Let's go ahead and let's draw a base plate here. So we'll use the rectangle. I'll just arbitrarily come over to some point on the grid and click. And then click on that same point on the opposite side to complete it. Now if we run this simulation, as we've seen before, all these objects will just simply fall with gravity. So we need to begin anchoring things down or restraining things. To start, let's come over to the object toolbar and let's click on the anchor tool. If we want to do multiple anchors, for example, if we want to anchor this body and this body, we can simply double click the tool and it will keep it in that mode until we tell it to exit. If we single click the anchor over here on the toolbar, it will apply the anchor, and then when we're done with that first anchor, it'll turn the mouse back into the select cursor. So we've double clicked the anchor because we're going to apply an anchor to this body here and this body here. It doesn't matter where exactly you apply the anchor, just as long as it's over the body somewhere. So now notice that the cursor is still in the anchor mode. To exit this mode, we can simply select the arrow button up here on the view toolbar. If we run the simulation, now we have gravity, we have collisions between bodies, and we have those other two parts remaining fixed in space. What we'll do next is begin adding constraints to constrain this horizontal platform and the two bodies on the platform. Let's start by selecting the pin joint, and we'll move the mouse and hover it over the base of the horizontal block, which is also the apex of this polygon right here, and we get a snap point that wakes up. Click, and we've created a constraint right there. Just to verify, we can run it. Sure enough, it's constrained properly. Let's reset the simulation, and let's go ahead and let's add rigid joints between this block and this plate and this block here and this plate. We'll click on the rigid joint tool, move the mouse over the base of the rectangle here, and click. Click on the rigid joint tool again, and add that constraint there. So now if we run the simulation, just to check our constraints, everything's looking good so far. We'll stop, we'll reset. Now that the bodies are constrained, what we're going to do now is create slider controls that allow us to move this block along the platform to different positions, as well as this block here. So let's go ahead and let's select the rigid joint right here, attaching these two bodies together. I can see over in the properties window that there's 2 points that make up that constraint, point 12 and point 13. I'm going to go ahead and I'm going to find point 12 in my drop down list here, and I'm going to select it. With that point selected, I'll click on Define, New Control, Offset. By default, it will create X and Y sliders so that I could also vary the Y position. I'm not interested in doing that. It will always remain at the 0 position in the Y direction, so I can simply select that slider and press my delete key. I'll click on the slider, hold my mouse, and drag it over here so it's approximately over the center of this block, so I know that this slider is associated with this block. Notice when I selected this slider, the properties for that slider appeared over here in the properties window. Let's set minimum and maximum bound conditions for this slider control. If I look down on the ruler here, I can see that I want that block to probably not exceed maybe 4 meters in the negative x direction and maybe negative 2 meters somewhere in here in the x direction. So let's set the minimum and maximum boundaries accordingly. We'll say -4 for the minimum and -0.2 for the maximum. If you'd like, you can also set the number of snaps here to control the increments in which the slider will move between those upper and lower bounds. To check the slider control and its operation, and if we've defined it properly, we can simply click on the slider and drag it. And we can see that that block is remaining constrained to that platform and moving between the boundaries that we set it. Let's go ahead and repeat the process for this second block right here. Like we did for the first, we'll simply come over and we'll select that joint. And we can see that the joint is selected through the properties window. We'll identify the base point of that rigid constraint, point 15, select the drop down, and select the point from the drop down. That point is selected now. We can click on Define, New Control, Offset. Again, we'll remove the Y slider, click, hold, and drag the X slider, and we'll set the upper and lower bounds for this slider control. The maximum bound will be 4, and the minimum will be 0.2. To check it, move the slider and make sure that the block is staying constrained to the platform and moving along the X direction between the boundaries we set. So that looks good. Next, we'll bring in pictures and attach them to a couple bodies in our model. This procedure is not necessary. It simply adds a little character and realism to the model and can be more attractive depending on the age group that's using the software. I've already opened up a couple pictures and I'm going to access them. I have one called a hand. I'm using QuickTime Viewer for this particular image. I'll choose Edit, Copy, click in the Interactive Physics background, and then choose Edit and Paste. Next, I want to move the object over to the body I'm going to attach it to, and we want to size it down so it's approximately the same size. So I'll just move this to get it approximately the same size here, maybe a little bit less. With that body still selected, I'll press the Shift key, select this block, and then we'll choose Object, Attach Picture. Now it looks like that hand is really attached to that platform. As we move the slider, it will move along with it. We'll do the same thing now for this block over here. I've also opened up another image that I'll access here called a mass. I'll choose Edit, Copy. Again, click in the background of Interactive Physics and choose Edit, Paste. Like we did for the first, let's scale it so that it's approximately the same size of the object we're going to attach it to. That looks pretty good. With this object selected, I'll hold the Shift key, select another object here, the block, choose Object from the menu list, Attach Picture. Use the slider to check. It looks good. Now there are different ways to model a lever system. We can have the same lever arms and vary the forces. We can have the same forces and vary the lever arms. For this particular example, we're going to have the same value for the forces on each end, and we're going to vary the lever arms. Remember that there's a block underneath this hand. So we're not actually applying a force at this point in the simulation. We're simply using the mass of the block to cause this platform to tip to this side. If we click on this body right here, we're actually, when we click on it, we're not selecting the picture at this point. It actually, by preference, selects the block. We notice that over in the properties here, that when we clicked on this, it chose body 3. Currently, the mass of this body is 1.5 kilograms. We're just going to change it to something arbitrarily. Here, we'll say 10 kilograms. And we'll click on this body here, and we'll set it to be the same mass. So now that if I move the sliders to be equal distances here, we'll say 3.5, and I'll click in here and I'll say negative 3.5. I should have a perfectly balanced system. So if we run the simulation, we can see that the times and frames are advancing right now, but nothing is happening. We're in perfect equilibrium. Let's stop the simulation and reset. So to demonstrate our lever principles now, if we move the slider and run the simulation again, we can demonstrate our mechanical advantage here, or at least begin to. Let's select reset, and let's set the increments of our sliders to be something nominal so that they move in, say, increments of 0.2. So to do that, we'll simply click on the slider. Earlier we mentioned that we can specify the number of snaps for the position increments. We'll specify 19, which should allow us to move these sliders in increments of 0.2 meters. We can see that it is working that way. So we'll click on the next slider. Also define this as 19 snaps. And we can move the slider in 0.2 increments. Notice when I did this just a minute ago, I also clicked in this field right here and just typed in a value. That's also possible. Now in interactive physics, we can create meters and output vectors for just about any characteristic that we'd like. And we can do this for things such as springs and dampers and pulleys and bodies and things like that. So if we simply click on a body, for example, I'll click on this block right here, and then I'll click on Define, Vectors, Gravitational Force, and then I'll do the same for this body over here. Select it, Define, Vectors, Gravitational Force. If I run the simulation, okay, it turned on these vectors. Now let me reset these and let's scale these vectors down. Right now they're scaled large. It just depends on the size of the geometry that's drawn initially. But we can change that length. So we'll click on Define Vector Lengths, and we'll change these force vectors to something smaller, say 0.005. Select OK, and now we can see that we have both a numerical readout on the vector, plus they've scaled smaller. So if we replay this, so this is good. It gives the students a visual as to the system and what's occurring overall, and basically a free body diagram, if you will, of the entire system. We also mentioned we can create meters for different things. For example, if we select this plank here and then click on Measure, we can see all these different characteristics we can plot for this body. Let's click on Position and Rotation Graph. By default, a graphical form of this meter first appears. If we select the arrow in the upper left corner, it'll change to a solid bar graph, which we would see when we run the simulation. If we click it again, it changes to a numerical readout. Click it a third time, it changes back to the graph form. So just for quick demonstration here, let's go ahead and show how this works. If we want to resize this meter, we can click on one of the grips in the corners and drag it. And if we go ahead and run the simulation and stop, we can see that our meter is created here, and we have a little tracer dot that follows along the meter. So when we replay the animation, we can see what meter position corresponds to which model position here. Earlier we talked about how we can calculate the mechanical advantage of a lever system using one of two methods, either the force method or the arm method. we're going to use the effort arm and the resistance arm in this example. Since we don't readily have available a mechanical advantage meter from our menu here, we're going to go ahead and we're going to customize this meter to represent mechanical advantage. And we can use the slider values to do that. So if I click on this slider right here, I'm interested in obtaining the ID for this slider. This slider over here for the input is called, or for the effort, is called input 19. For the resistance, it's input 18. So if you can imagine going back to our formula for the mechanical advantage using the arm method, all we need is simply input 19 divided by input 18. No matter where we move these sliders, the meter will automatically reflect that data no matter what. So we can click on the meter right here. When we click on the meter, the properties over here shows us the data for the meter. So the formula that's currently being used in this meter is the formula to return the body 1 position rotation. What we're going to do is we're going to simply click with the mouse, drag it and highlight that entire expression, and then press delete. Next, we'll type in our own custom expression, and it will look like this. First, ABS, which will be absolute value, and we need that because we have a negative over here for this slider. Begin parenthesis, and then we'll type in input bracket 19 bracket divided by input bracket 18 bracket, end parenthesis. So we're simply dividing the effort by the resistance and then taking the absolute value of that entire expression. And then for the name of this, we'll just title it MA for mechanical advantage. Time is not relevant here since this is a constant number that will be returned. If we come over to the meter now and we click anywhere outside of this properties window, notice that it immediately updates the title in here. And then if we click on the arrow tool, we'll go to the numerical readout. And we can also rename this. I'll show that in just a moment. But if we go ahead and we run the simulation and stop it quickly, notice that it immediately shows us the mechanical advantage of the system. Another feature we have here is the ability to show all the initial conditions and have them displayed in the meters before we press the run button for the simulation. So notice in our last example, we had to press the run button to then display the mechanical advantage of the system. Well, if we click on World Preferences, we have an option here to calculate initial conditions automatically. If we select that and then select OK, all the conditions will be displayed initially in the readouts if we make a model change. So for example, if we move the slider here for our resistance, notice that the mechanical advantage updates immediately to reflect what the advantage of the system is. So we know right away if we're going to get an advantage or a disadvantage in the system. There are some things we can do to make the model slightly more visually appealing. For example, we can change the title of this meter, we can change the color of the meter, we can change the colors of the bodies, we can also hide the different constraints, and we can change the font size here of the different sliders and the readouts and things like that. For example, let's reset the simulation here. We'll right click on this meter here, choose Appearance, and we can change the title right here to anything we'd like. We can also change the color by selecting the color. We can click on a body and we can change the body color too. If we want to change the font size, we can select the object whose font we would like to change and then click on Object, Font. Maybe we'll give this a size 11 and we can get those to increase in size. We can also hide these constraints. So if we drag a window across those three simultaneously and then choose Window, appearance. We can uncheck the show button, and we can do the same for our rigid constraints and hide those. So it just cleans the model up a little bit more, makes it a little more pleasing to look at without all the constraints and things like that. Now, we mentioned before there are two different approaches to calculating the mechanical advantage of a lever system. One being using the forces and the other being using the moment arms, which is what we did in this example here. Let's show how we can modify this model pretty quickly to move from using the moment arm method to using the force method. Recall that we set the mass of this block underneath this hand to be the same as this mass over here. Well, we're going to double click this body, and we're going to set that mass to be something much smaller, say 0.001, so its effect on the mass portion of it is negligible. And then we'll click on the force tool here, and we'll add a force on that body. It uses Cartesian coordinate system by default. We can also specify polar. We'll tell it to rotate with the body. If we click on it there, we can see that it will rotate with the body. That means that when this platform tips, this force will always remain perpendicular to the face of that platform. So what we can do is also define a slider control for this force, just like we did for the moment arm positions. We'll click on, with the force selected, we'll click on Define, New Control, Y Force. We can specify an upper and lower bound for this force. Negative meaning pointing in the downward Y direction. We can also specify any number of snap increments we'd like to. Let's go ahead and click on this block over here, or this body underneath this mass picture, and we'll click on Define, New Control, Mass, and now we have a mass control slider for that body there. We can also specify the upper and lower bounds for that mass. So now if we set the moment arm distances to be the same, so for example 2 and -2, our system is purely being driven by the difference between the mass and this force. This requires a little more thinking by the student and predetermination. If they're determined to determine the mechanical advantage, they have to also take into account gravity in this situation, because on one side we're using mass and on the other side we're using force, and this value is in newtons. So if we run the simulation, we can see that that tips to one side, so the input has a greater advantage. Now if we run this again, now we're running the simulation. We can see that our cursor looks like a stop sign here. If we move these slider values, they'll change in real time during the simulation. So a student could actually have fun and try to balance the system out until they get to the equilibrium position. And I accidentally stopped my simulation there, but you get the idea. Now we also have this meter up here. This meter is not reflecting the current mechanical advantage. It is based off of the moment arms right here. Recall that we customized it. So what we can do is we can either create a new meter, or we can customize this one to reflect the mechanical advantage being based off of the forces. So the first thing we do is determine what our resistance mass is right here, which is input 26, and our effort force, which is input 25, and we're going to use those two IDs in this meter just like we did the first time. Click on the meter, and here's our formula. So this time we're going to have to take into account gravity in conjunction with this mass right here. So what we'll do is we'll say 9.8 times, and then we'll simply change the ID from 19 to 26, and then we'll change this ID to 25. So we're multiplying gravity times the effort, or excuse me, the resistance mass, and dividing that by the effort force. And we also have the absolute value, which we need in there because this force over here, or this mass, could potentially go negative if we didn't set our slider bounds properly. but in this case it should be okay with or without. If we run the simulation, we can see our mechanical advantage changes to reflect that. And it also changes in real time as we move these slider controls around. The last thing we're going to do for this demonstration is show how this model now can be saved in player-only mode. This is a great way to let the students interact with the model but keep them on task. They will not have access to any of the constraints or underlying features in the model, and they won't be able to change anything. To do that, we simply click on Edit, Player Only Mode, and then we can choose File, Save as Player Only. I've already done that, so what I'm going to do is I'm going to open up a model that's in player only mode, and this is exactly what it looks like. So the student would open the file, this is all they would see. They could run the simulation, they could interact with the sliders, and they stay on task with the objectives of the assignment. This concludes our demonstration of interactive physics in creating a simple machine of a lever. If you have any questions, please find the contact information on the closing slide and feel free to contact us with additional questions. Thank you.